So good morning, everyone. Welcome to this edition of Data at Breakfast. I apologize for the wrong background, but I noticed it's too late. This morning, I'm very happy to, to introduce Professor Yin-Zhe and his postdoc, Dr. Wei-Ming Dai, who will speak about who will solve for us, hopefully, the puzzle of the Hubble constant, yeah, which is based on recent work that they recently published. Yeah. On the panel, you see also Professor Kabilan Mudli, who is also working in astrophysics, and he kindly agreed to moderate the question and answer session after the double presentation. And as usual, Professor Ilya Sinaisky is on the panel because he always kindly acts as co-host of the event in case there is some ESCOM or internet trouble, so that we have two independent hosts for this event so that nothing can go wrong. So Yin-Zhe, we are very happy. Sorry, let me introduce in a few sentences Professor Ma. Professor Ma, I think if I remember correctly, so I need to check, completed his PhD at the University of Cambridge in 2011 and had then a few postdoctoral positions at the University of British Columbia and at the University of Manchester before joining UKZN. And Dr. Wei-Ming Dai is currently a postdoc in the group of Professor Ma. So Yin-Zhe, people are here to listen to you, not to me. So if you would like to start sharing your screen and starting your presentation, you are most than welcome. And while you do that, the usual reminder to the participants, please make use of the Q&A facility at the bottom of the screen to ask questions, and Professor Mudli will then organize them in a coherent way and present them to Yin-Zhe. And since we are not too many, if there are urgent questions, please raise your hand and we can give you at the end the opportunity to talk. Yeah, so Professor Ma, please, it's your show.
Oh, thank you, Francesco. Let me share my screen. Okay, I guess you guys can see my screen, right? Just to check.
Yes, and there is a movie. Well done.
Yeah. Oh, right. Yeah. The movie shows the scenario if you travel in the space in the universe. So the universe is very big, actually much bigger than what we think. Right. So today I'm really happy to talk to you about our recent work on solving, provide a potential solution to solve the Hubble tension. So this is the work that I've done with my postdoc, Dr. Dai, who will speak in about 20 minutes, and also with another professor, Hongzhen He from Shanghai Jiao Tong University in China. So we started the idea in the late of 2018, and we consolidated, and then started in 2019, and then we consolidated and published last year, right, in the Physical Review, the Rapid Communication. Okay, where did the whole story start from? Let me click on this. Okay, right. So the whole story starts from Einstein. So from Einstein's theory of relativity, which was published in 1916. So you can see this is the relatively young Einstein, and he published that in the German journal. And the most important result from his publication is the Einstein's equation, which is showing here in this very abstract way. So basically, on the left-hand side of the equator, this is space, and on the right-hand side, it is matter. So the matter and space in Einstein language are coupled to each other. So in John Wheeler's sentence, the matter will tell how the space would curve. On the other direction, the space will tell how the matter will move. So that is basically the essence of general relativity. The space and matter are kind of strongly connected to each other. So later we will see this in our particular example of holographic dark energy, and to see how that will shape the evolution of the universe. And from this, you actually, after Einstein published his theory of relativity in 1916, he started to think about how to apply that to the entire universe, because theory is theory. You want to apply the theory into some realistic object to test its behavior. And so he thought that the universe should be static, whereas in contradictory in 1929, as you can see, this gentleman called Edwin Hubble, who was an American astronomer, discovered that the universe is actually expanding all the time rather than static. So the way he discovered this is to observe a whole set of distant galaxies and measure their velocities as a function of distance, showing here in this plot, and plot their relation between velocities and distance in a simple graph. So therefore, he was able to mark this dot on this plot, and then he found, yeah, there seemed to be a simple linear relation between the two. If you draw a straight line from the left lower corner to the right upper corner, it seemed to be a straight line that going across these points, even though there's a lot of scatter in between. So therefore, he wrote down this very simple equation called V equals to h0 times d, where the V is the receding velocity of the galaxies. They are all moving away from us. And the d is the distance. He found a one-to-one correspondence, a linear relation between the two, whereas the coefficient he defined as the Hubble, and he defined as a constant, but later it's called Hubble constant to honor his name. So this tells you that the further away that the galaxy is, the faster they are moving away from us. There is a one-to-one corresponding in between. So if you heard about this at the for the first instance, you may think about we are actually in the center of the universe, but this is a wrong thought, because even though galaxies are moving away from us, they're all moving away from each, in between each other. So actually the universe is actually expanding rather than moving just away from us. So the good way to think about this is through a graph by a Dutch artist called M.C. Escher. So this is one of my favorite art, which can really beautifully show the idea of cosmic expansion. So you can see that in this piece of art, he drew this different rod, and they are connected to each other. Actually, the expanding universe can be conceived as the length of the rod being lengthened out, being expanding all the time. So each of the knots will be further away from each other, but there is no center of the universe. So we are not at the center of the universe. So I think this would really give you a good picture of what does the expanding universe really mean. Okay, so in the previous plot, I have defined what is the value of h0, which is the Hubble constant. And that is actually one of the fundamental parameters of the universe, because that really tells you how fast the universe expands. So measuring that parameter is crucially important in terms of understanding the fundamental nature of the universe. So people have started this entire enterprise of measuring it from the early time. So, so this is what they have found, or what they have been measured, right? So this is the value of the h0 as a function of publication year. You can see that at around 2000, which was already 20 years ago, the error bar, or let's say the uncertainty of that value is really large, so that whatever the measurement is, they are all well consistent with each other. So, but as the time goes by, as the publication year approaching now, 2020, you can see that gradually there are two groups measuring that h0 value and approaching different values. So one group is the blue band, which is showing in the upper branch, showing h0 value to be a higher, prefer a higher value, roughly about 74 kilometers per second per megaparsec, where the megaparsec is really a huge astronomical unit, equals to 10 to the 24 meters. Okay, whereas the red band, the red branch, basically approaching a lower value of h0, and it's gradually approaching a value of 67. And as the measurement goes on and on, become more and more precise, these two measurements become too discrepant towards each other. I mean, against each other. So there is a puzzle here, right? Why one measurement give a higher value, whereas the other measurement give a lower value? There's something wrong here. There's something that either one of the experiment is wrong or our understanding of the entire universe is wrong, right? And I think that is really the core of discussion today. And I can show you that what is the current status is. So you can see that on the upper right corner here, where you can see my mouse, it is a measurement from the microwave background, cosmic microwave background radiation, which I will explain to you in a minute. And that really relics from the Big Bang, the photon that really left over from the hot Big Bang of our universe. And that gives you a low value of 67. Okay, but the others, which are measurement of our local universe, things like the time delay cosmography, which is a measurement of the astronaut through the strong lensing, or the others, Cepheid distance, distance ladder plus supernova, would prefer a higher value of astronaut, which really being consistent with 74. So that's making the two camps to be distinguished from each other, and really prefer two different values. Okay, so before I tell you my solution, let me explain to you what are these two camps of measurement of this Hubble constant and why they are. So one thing is the local measurement, which is showing here in this horizontal bar here, right? So that local measurement is the distance ladder measurement, which is actually very simple. So we use geometry to calibrate the pulsating stars Cepheid variables, which is showing here as the distance ladder 1, and then calibrate the exploding stars, and then type 1 is supernova. So in details, it is a technique of nested 3 rung of ladders, right? When you climb on the ladder, you need to step onto rung by rung until you reach the top. So the first rung is really close to our solar system, and that is 5 independent geometric sources to calibrate the luminosity of the Cepheid variables. And in the middle rung, we use Hubble Space Telescope to observe the Cepheid variables in the host of 19 recent type 1a supernova to calibrate them. So we use our geometric distance to calibrate the Cepheid variables. And then once that is calibrated, when we search for the other galaxy which contain both the Cepheid and type 1a supernova, to be able to calibrate the type 1a supernova luminosities. And then once we get this calibrated, we go out to a larger distance and then find more distant supernova, and then to measure their distance and then against the redshift. And from here, we can really going out to the really large space, and therefore to measure the expanding rate of the universe, which is h0. And we get 73.5 plus minus 1.4, a total uncertainty of 1.9%, right? Okay, this is the local measurement, which is prefer a higher value. And then what about the early universe measurements? What about the CMB measurement? And that's really coming from measure the relics of the Big Bang, which is really something significant, right? So this is the CMB fluctuation. Actually, this is the fluctuation of the entire universe when the universe was only 380,000 years since the Big Bang. Okay, so what is the age of the universe right now? It is 14.7 billion years, and 14.7 billion years, whereas this is only 380,000 years since the Big Bang. So this is really, really at the baby period of the universe. And you can see that it was all just very hot and very dense. And this color means the density fluctuations, or let's say the photon temperature fluctuations across the whole sky. Okay, so to understand this, let's think about what would happen if you have a mixed plasma of a mixed fluid of dark matter, gas, photon, and neutrinos, and they will propagate it at a speed of sound from the very early time up until that 380,000 years, where the temperature dropped down sufficient low so that the photon decouple from the hot plasma. It's like if you have a party that many people are kind of bumping into each other, but if the size of the room is expanding all the time, then the probability of people bumping into each other will be dropping and dropping until at some point, nobody will bump into each other, and we say they are actually decoupled. Right? Okay, you can see that because of this propagation of the acoustic wave, the photon gas propagated to a distance about 150 megaparsec away from the center of perturbations. And we can see actually such effect actually happening all the time in the universe. As the baryon, we call it baryon acoustic oscillation. It's actually the propagation of sound wave at the very beginning of the universe, from the Big Bang all the way up to 380,000 years. But in the universe, where there are not just one point of random perturbations, there are many of such perturbations. So eventually we see a stacked image of these early fluctuations of the universe. Okay, this is pretty much like if you have a quiet water pond, and then you drop a stone, and the stone will make ripples, and that ripples will produce hot and cold rains around each other, and they will be propagated at the speed of sound. So, but unfortunately, in the universe, it's not just one. Let me just replay this. It's not just one stone, but many stones, many random stones, many random fluctuations. So eventually, you see overlaid image of hot spot and cold spot, which is really part of the sky that we observed. So this is what we observed. This is exactly what we observed by using both WMAP and Planck satellite. Okay, so now the question is, can you reconstruct that ripple? Can you reconstruct that ripple of random fluctuation at the early universe, right? The answer is yes. Actually, you don't need to do too much work to see this. So if you have a full sky and you take out all of the hotspot and you cut it down, all of the hotspot little patches, and you average them, you add them together, you will see something like this. You will see that around each of the hotspot, there's a cold rain. And around each of the cold spot, there's a hot rain, right? That is the ripple made by the universe itself when it was only 380,000 years, right? And you can see that effect also shown in the European Space Agency's Planck satellite. So I have been working on this for many years since my PhD. And it's such a joyful experience to see that the new experiment produce something consistent with previous experiments, right? So this is really confirmed. This is the sound wave information that happened in the early universe. Okay, now we can see why we can use that to measure the expansion rate of the universe. Because if we have a fixed ruler and that ruler size is 150 megaparsec on the sky, and then if that ruler is close to us or further away from us, so let me use my pen as an example. If that pen is close to us, then my angular size will be larger. But if that pen is moving away from me, then my angular size is smaller, right? So if you can measure the angular size of this ruler, and then you know the RS, you know the size of the ruler, then you can measure the distance between the observer to that last scattering surface. So that distance is called angular diameter distance, shown here as a dA, and we can use that to measure the value of Hubble constant, because that really depends on how fast the universe really expands. So we measure that H0, and that really gives us a value of 67 kilometers per second per megaparsec, right? So which is lower value than the local distance ladder measurement. So these two values are really distinctive from each other. Okay, so now the question is, why is this? And what is the solution of that? Okay, so first of all, you can argue that some of the experiment is wrong. I mean, either the CMB, either the cosmic microwave background experiment is wrong, or you can say the local distance ladder measurement are wrong. But bear in mind that each of the measurement actually supported by a whole bunch of other measurements, which are independent in terms of systematics and also in terms of the calibration and so on. So therefore, the probability of one camp is totally wrong is not that great. So then we have to think about something else. Maybe our understanding of the entire universe is wrong. So I call it new physics. And yes, I mean new physics, not some hand-wavy phenomenological alternatives or arbitrary parameterization of dark energy, but something new, something that really new, something that invoke new thinking. Okay, so therefore, from the year before last year, the 2019, I started to scratch my head and thought about new physics, and then we tried to build our solution based on the holographic principle of quantum gravity. Well, oh, that seemed to be horrible. That seemed to be scary, right? What is that? So holographic principle to say that the information associated with a certain part of the space may be representative as the bits, bits, which is the quantum information on the surface surrounding it. In other words, the quantum states are described by variables on the surface. So in 1990s, there was this great physicist, 't Hooft and Susskind conjecture that the total degree of freedom of any effective field theory in the box of size L must be below the black hole entropy of the same size, which is we call duality connecting the ultraviolet scale, which is the microscopic scale of fluctuations, with the infrared scale, which is really the size of the universe, which connect the quantum fluctuation at microscopic level with entire universe in the infrared level. So this is the 't Hooft and Susskind duality, the holographic duality. Okay, but then later on, this whole bunch of authors in 1998 found that if that equation is true, then there could be many states where its Schwarzschild radius, which is the size of the black hole of it, would larger than the box of L, so that they will actually collapse and non-exist. Therefore, they revised that and to produce an upper bound for this, right? And then what we did, I mean, what Professor Lee did, who was one of my mentors before, and also I followed a paper in 2009, which is already 12 years ago, is that we saturate that bond by adding into one free parameter c. Okay, this c is not the speed of light, 3 times 10 to the 8 meter per second. This is not. This is just a free parameter in between 0 and 1. Okay, so we're adding into that free parameter and saturating that equations, and we derive the holographic dark energy densities. And so this is, we believe it is any density of the dark energy which dominate the evolution of the universe. So in brief, okay, this seems to be all mathematical and seem to be dazzling to some of you maybe, that we actually make two explicit assumptions. So one is that the holographic principle, which apply to the black hole, also apply to the entire universe. Okay, that is crazy, isn't it? But okay, it might be crazy, crazy enough to be true. Okay, so the box of size L should be related to the horizon size of in cosmology. And the other thing is the dark energy is indeed the quantum zero energy fluctuations, right? So this is the assumption behind this formula. Okay, so then. Then we plug that equation into our evolution equation of the freedom equation, which Dr. Dai will show in a minute, and we will solve this equation of state evolution of this function. And you can see that the equation of state of this dark energy is always evolving, whereas Einstein's lambda, Einstein's cosmological constant, is always -1, which is a horizontal line here, right? So therefore, this model is generically different from Einstein's lambda. So it could be, it's actually distinguishable from Einstein's model. And then also in comparison, we also basically plot two other parameterization of this model. So which has large more parameters than this holographic model, which only have single parameters. Okay, so you can see that their equation of state of holographic dark energy is something that is transiting. It from a larger value go to a smaller value, right? And that's really something feature that we want to use, because certainly to solve the Hubble tension, we need to have a really fast expanding at local time, whereas the distance to the large scattering surface need to be fixed to be relatively high precision. So we need the universe to expand a little bit slower at the beginning, and then expand faster later on. Okay, so I don't know whether you have that experiences. If you see a marathon runner, sometimes they run at a constant speed, but some of the marathon runner they run very slow at the beginning, and then they accelerated, and then eventually they surpass all of the people and win the match, right? So maybe our universe is like some of these marathon runner, which run quite slow at the beginning and comparatively slow at the beginning and accelerated even faster at later time. Okay, so so this is basically my simple introduction of the whole work. So and then we basically plug that equation into Friedman equation and solve it, and then obtain our result. And then Dr. Dai will just show you now that how does that solve the Hubble tension. So now I hand it to Dr. Dai. Okay, Dr. Dai, can you share your screen?
Yes. Can you see my screen?
Yes, yes.
Okay. Good morning, everyone. My name is Wei-Ming. I'm postdoc at the University of KwaZulu-Natal. It's a great pleasure to be here and speak as the second part of this talk for the Professor Ma's talk. And this is a work that I have done with Professor Ma and Professor Hong Jianhe from Shanghai Jiao Tong University. In this second part, I will analyze the evolution of holographic dark energy and the constraints from observations. But firstly, I would like to briefly introduce the framework of modern cosmology. This will lead some equations. As Ma said in the first talk, the fundamental of modern cosmology is Einstein's general relativity, which connects the space-time and the matter-term. G mu is the Einstein tensor. Lambda is the Einstein cosmology constant. The space term equals the mass term in this equation. In the universe, the mass components are described by one tensor called stress energy tensor. The homogeneity and entropy on large scale leads to the maximally symmetric FLRW metric. That is the G mu nu matrix. -1 is the time term and A square is the space term. A is the scalar factor that indicates the size of the universe. Here we only consider the spatially flat universe. When the FLRW metric is applied to Einstein equation, the whole equation can be reduced to two simple equations. That is the first Friedman equation and the conservation of matters. Here the capital H is the Hubble constant, and rho is the energy density of universe. Other terms are just constant, of which capital G is the neutron constant, which is just a scalar, not the Einstein tensor. And the notation P in the conservation equation is the pressure of matter. Using those equations, one can infer that the universe is extremely hot and dense in the beginning and gradually expanding to the current universe, because from the Hubble's measurement, the universe is expanding, and if we go to the very early stage, from that two equation, we can find that the universe become more and more dense and hot. This concept is the Big Bang of universe. In this process, the value of Hubble parameters determines how fast our universe is expanding, and as the plasma cools down, photons and baryons decouples at the age of 380,000 years. The relic radiation can be detected today, which is 2.7 Kelvin CMB background. This background was detected by Penzias and Wilson in 1968. This is an important evidence of Big Bang. Theoretical prediction of the thermal history of our universe was made based on the measurement. The last scattering surface of photons and baryons are estimated around this dashed line. If we convert it to time, and this is very close to today's measurement. But this just use the background information. But the signal is so uniform that only 2 decades later, the temperature spectral fluctuation of CMB is detected for the first time by Kobe satellite. And 1 decade later, the success of Kobe satellite launched by NASA provided a high resolution of the full sky CMB signal. And later, Planck satellite improves the signal to ratio and provides high angular resolution. You can see we already have a high precision measurement of the cosmic microwave background radiation from early years. So fluctuations in CMB are at the level of 10 to the -5. To understand the whole story, we can simply study the linear observation of Einstein equation. That is to add the linear terms in the metric and stress energy tensor. They are the perturbed diagonal term and off-diagonal term. If we compare this to the GNU metric, we will see the off-diagonal terms. And if we compare this to the tensor matrix we showing before, we see this preservation of diagonal terms and the off-diagonal terms. We will solve those equations, but because the metric and the matter are coupled to each other, the linear theory is described by the Boltzmann equations decomposed to the Fourier modes. The evolution of Boltzmann equation highly depends on the attributes of each component. For example, the collision between photons and baryons has to be taken into consideration. And on the other hand, for neutrinos and dark matter, they are collisionized. But all these terms will couple to the curvature perturbation. Therefore, we have to solve the whole complicated differential equation to get the perturbation of CMB photons and then eventually get the CMB power spectrum. The evolution of this Boltzmann hierarchies needs to be numerically solved. This is just a slide to show how we did and what we will get. We use lasers, lambdas, lambda online tools. Although the universe is complicated as we has introduced, the cosmology model can be relatively simple. As an example, one can input the 6 parameters of lambda CDM model on the webpage of Lhasa Lambda. Just in 3 seconds, we will get the power spectrum of CMB. These results show the auto power spectrum of temperature in the first panel and the cross power spectrum between temperature and the E-mode polarization in the middle panel, and the last panel is the auto power spectrum of E-mode. This is just one realization of the model. To constrain the model, we will compare the model with data by many realizations with different parameter values. We vary these model parameters and generate the power spectrum, and then fit the power spectrum with Planck data by comparing the likelihood. We use the Bayes theorem to predict the parameters of a model. Bayes theorem describes the probability of an event given the data. That is the first equation. Here D is the data. W and sigma are 2 parameters. Here we just simplify the parameters to 2. The probability of parameters occurring given the data is the left-hand term equals the probability of data given the model times the prior of the model parameters, and then divided by the a constant. This is from the measurement of this is data. Let's say the probability of parameter given the data perpendicular to the likelihood, which is the P in the Bayes theorem. But in terms of the parameters, we call this likelihood of the parameter. And the constant coefficient in the equation doesn't affect the determination of model parameters. When we obtain the posterior distribution of the parameters, we can get the marginalized posterior of the parameters of interest by integration of all the other parameters here. Here we integrate over sigma to get the predict of W. In our case, the holographic dark energy model, we are interested in the Hubble constant and the parameter of holographic dark energy. Here is the model. The SD cosmology has 7 free parameters, which are dark energy density, baryon density, angular acoustic scale, scalar spectrum index, amplitude of primordial propagation, optical depth, and the holographic dark energy parameter C here. AS and NS are the observation parameters. All other parameters are the background parameters. In order to estimate the distribution of parameters, one need to explore the parameter space. Here is in our model is the 7-dimensional space. This can be done on evenly spaced grid, like the one showing in the red panel. But for high-dimensional model, it is unfeasible. The Markov chain Monte Carlo technique allow for efficient determination of best fit parameters and error bars for complex electrical and high-dimensional models. It samples more points in the high probability region of the parameter space, and samples less in the low probability region. For instance, the SD model, we run the MCMC code, and the chains can normally converge in 1 day. But if we explore the whole space, parameter space, to explore the data, and if we just take 100 points along each parameters, this would be 10 to the 15, and we will take 1 million years to finish the exploring of the parameter space. That is unfeasible. Follow the process above. We will solve the background of SD cosmology first. In the holographic dark energy, the energy density is related to the event horizon L, as explained by Professor Ma. In contrast to the matter and radiation terms, SD's energy density is coupled with Hubble parameters. Here we substitute L to this expression. We say the integration of Hubble constant here. We need to we need to solve the energy density of Hubble holographic dark energy numerically, and solve the Friedmann equation here. Then we can get the power spectrum and eventually get the parameter estimation. This is a slide showing the background evolution of holographic dark energy to be numerically solved. I will go to next. Then after solving the equations, we can get the HD, the equation of state, W as shown in the left, which was a function of redshift Z. And it changes from a reading above -1 in the early universe to a reading below -1 in the later universe. On the right-hand side, we plotted the evolution of SD energy density and the total energy density, which is rho critical here. For the energy density, HD is negligible as high Z as usual, as same as other models. But after reaching the minimum, it's HD, the energy density bounce back. This unique evolution of the equation state and the energy density is very distinguishing feature of this model. Using the MCMC technique, we constrain the holographic dark energy parameters C and the Hubble constant H0 with the CMB and BL, and compare the estimation to the local measurement. From the 2D counter in this color, we can see that the SD favors high Hubble constant, which means it is consistent with the local measurement about 74. That is because the holographic has a slow evolution at the beginning and a faster evolution later. So that it will make the local universe expand much faster, whereas keep the angular diameter distance to the last scattering surface to a fixed value that is determined by the CMB measurement. In the lower right panel here, we also consider Hubble parameter between the compare Hubble parameter between the holographic dark energy and lambda CDM, which are the blue band and the gray band, in a range from 0 to about 10. Where you can see the holographic dark energy can fit the data at a high redshift and cover the local measurement of Hubble constant from distance ladder measurement, whereas the lambda CDM cannot, as is shown in this gray band. We made a combination between SD, CHASD, CPL, and lambda CDM. CHASD and CPL are parameterized model that was added to mimic HD. Compared to the lambda CDM model, HD has one extra, we can say one extra parameter. CPL has 2 extra parameters, and CHASD has 4 extra parameters. We introduced the archaic information criterion to quantify the goodness of fit by compensating the additional parameters in the models. Smaller ARC indicates a better model. One can see that the HD is better than lambda CDM in terms of the data ARC. The 2 parameters model, CPL and CHASD, have no deep physical origins. We want to see if this model can mimic HD and alleviate the Hubble tensing. In terms of these two requirements, as you can see in the red panel, the fitting of HD is the best of the four models. In this way, the holographic dark energy can largely solve the Hubble tensing. In the lambda CDM cosmology, there is about 4 sigma discrepancy between CMB infrared astronaut and the local measurement. We propose that holographic dark energy to solve the tensing, but the current data is not enough to verify or falsify this model. We look forward to test the model with future data. Dark energy's spectroscopic instrument is as seen here. Is the US ground-based telescope, which will obtain much greater number of galaxies to constrain the dark energy evolution from low redshift all the way up to the redshift 2, within which the models are sensitive to data. As you can see, SD and lambda CDM can be distinguished clearly in the low relative region. Other new problems will also improve the constraints, such as the SK project, some of whose precursors have been running in South Africa. Will also put strong constraint on Hubble constant by the technique called 21 centimeter intensity mapping. In the right-hand plot, the mock data of SK1 and SK2 demonstrated that the BAO from 21 centimeter intensity mapping can improve the constraints significantly. As we can see this in the blue and red counter. Another alternative way is using the gravitational wave measurement. Current gravitational wave measurement in the left lower panel shows the potential to constrain to put a constraint on Hubble parameters. Although this constraint is relatively insignificant compared to other data, but with more samples in the future, the constraint will improve further. In summary, the holographic dark energy is built on the holographic principle of quantum gravity, where the holographic principle applies to the whole universe. We demonstrated that with a single SD parameter, which is C, when it's around 0.5, is the equation of state changes from above -1 to below -1, which can largely resolve the astronaut discrepancy between CMB and the local measurements. We also show that for any value of C, the HDUS always evolve as a function of time and never mimic the Einstein's cosmology constant, which means this model can be substituted or falsified by future data. And the near future data, such as Daisy, Euclid, and SK, will have the significance to put much stronger constraint on the model. We will see whether HD model can eventually work or not. Thank you.
Yeah, thank you very much, Yin-Zhe and Wei-Ming, for the very exciting presentation. Congratulations for the excellent work. So we are looking forward to see what the next generation experiments will say. So good luck with that. Yeah. May I ask now Professor Moodley to start the question and answer session? And I see that we have already a few questions in the Q&A, but please, we still have a few more minutes to answer two questions. Kabilan, please.
Yeah, thanks, Francesco. So the first question comes from Serban Proches. And he's asking, it's a very interesting talk, but also very technical. So he would like you to summarize, what are the implications of the holographic model for the Big Bang itself?
Okay, so so yeah, the Big Bang is actually the whole scenario of cosmic evolution. It says the universe come from very hot and very dense beginning, and then it evolved and gradually expanding and gradually evolve. And then forming the structure that we are seeing today. So, so what is the implication of that? So major implication is at a later stage of this Big Bang model or the expanding universe. So the holographic doctrine is saying that the accelerated expanding was actually slower at the beginning, but faster later. So we should be able to see galaxies moving away from us much faster than the standard Einstein theory of the lambda CDM model. So in that sense, the implication would be if we live long enough, that long means billions of years long, that we should be able to see galaxies that are receding from us in a faster pace than what we could see before.
Okay, thanks, Prof. Ma. So the second question, which comes from Arun Bisham, is if you had to explain to a layperson how you would resolve the H0 difference, how would you do it?
I think that is I think I mentioned that in my part of the talk. So to resolve the H difference, the H difference is mainly that if we measure our local expansion is very fast. It's faster than what we expected. But if we measure this microwave background radiation, which is really the photon from the large scattering surface, then we see a low value of H0. So how to, in a layman term, that we need to make the universe expand faster at the later epoch, whereas keep the distance from the observer to the very distant universe to be the same, right? So to resolve that, we need the mechanism that can accelerate universe a bit, remodulate the acceleration rate, and making universe accelerated slower at the beginning and then much faster later time.
Okay, thanks, Prof. Ma, for that explanation. Then there's a final question from an anonymous person. How is the holographic principle extended from black holes to the entire universe? Is it possible that the holographic principle only applies to certain parts of the universe apart from black holes?
Okay, so right, so a good question. How is holographic principle extended from black hole to the entire universe? So yeah, we just extended. Yeah, basically. So we think that the holographic principle, which connect the fundamental scale fluctuation with the infrared scale, would applicable to the entire universe. So in some sense, this is a crazy idea, but as I said, it might be crazy enough to be true. So yeah, so we extended, we think the same principle would apply to from the black hole, also apply to the entire universe. And also because both the black hole and the beginning of the universe are all very quantized. So we use the same quantum gravity principle. We think they are applicable for both of the object and situation. And it is possible that holographic principle can only appear to certain part of the universe apart from the black hole. This need to be tested. I don't think we have a clear answer yet. At the moment, we apply it to the entire universe so that it will be testable if we derive the predictions.
Right. Thank you, Prof. Mafo and Dr. Dai for those presentations and the responding to those questions. I don't see anyone with a raised hand, or there's nothing in the Q&A. So yeah, I think we can wrap it up. I'm not sure unless there's final urgent questions. Thanks very much. Francesco, I'll hand back to you.
Yeah, thank you, Kabilan. Thank you very much. Yeah, if there are no more urgent questions, then it's just my pleasant task to thank again Professor Ma and Dr. Dai for the very nice talk, and to congratulate them again to the excellent work. And I'm really looking forward to see how this story evolves. Yeah, that will be very exciting to follow. So thank you very much for your time this morning. And I hope that your recent paper will receive the attention that it deserves. Yeah? And also thank you very much to the participants for waking up early this morning and being with us. And just a preview for next week, we will announce later today another exciting data breakfast for next week. And maybe just a suggestion to all the participants: if you would like to suggest speakers for the future editions of the data breakfast, please just drop me an email and we will see what we can do. You know, my challenge is that since we went online, we have the data breakfast almost every week. Yeah? And sometimes I have to think very hard to invite people and and bend the arm to come here to speak. So if you have suggestions, please feel free to drop an email to me or to Kimara, who is always acting efficiently in the background to make this happen. So thank you very much, everyone. Have a good day. Enjoy your weekend, and please stay safe. And hopefully we will all get soon a vaccine.